So the basis case will be, so the basis case will be, I'll just show that P1 is correct. Now inductive cases, this time I have two. One is if Pk is correct, then P2k is correct. Okay? Or perhaps, let me make it like this. Let's use 2 power. Okay, if 2 to the power k is correct, then n. Then, let me see, which one is better? K. Let's use k. So if Pn is correct, what would I use? I use k. Okay, sorry. If Pk is correct, then P2k is correct. Okay? And then the other one is, so this is about forward moving. And then the other one is, if Pk is correct, then Pk minus 1 is correct. Okay. So in that sense, we can show that, we can show what? Pn is true for every n is equal to 1, 2, 3, up to infinity. Reason, what is the reason? So first of all, just with the first inductive case alone, we have P1 already, right? So we know that P2 is okay. We know, because we know 2 is okay, then we know 4 is okay. 4 is okay, 8 is okay, 8 is okay, 16 is okay, and so on and so forth. And now, how about the intermediate part? How do I get 5 or how do I get 11? So for 11, then I can go to 16 and come back. And if you like, you may just go to 128 and go back. So after going back, you always hit 11, right? So because this one, so if I want to show that Pn is true for some non-2 powers, so what I'm going to do is I am going to apply this one enough number of times so that I get a number larger than n, a 2 power larger than n, to be true. And then apply this inductive case here to go back so that this is also true. Okay? And then, so this one has a special name. This one is called, so this is quite different from the previous cases. So this is called backward induction, because in this inductive case, it goes backward. So you may wonder what kind of proof looks like this. So one of the famous proof looks like this. It is called the AMGM inequality. We can prove the arithmetic mean is always greater than or equal to the geometric mean. Okay, so let me write down. So let's consider 2 numbers. Or let's consider a few numbers. Let's say 5 numbers. Let's say A, B, C, D, E. So we can talk about the average of this number, right? So what is the average? The average is, let's say we add them together and then divide it by 5. So that each of these average, so you can replace each one by the average. And then you add the average one by one together, then the total sum will be the same as A plus B plus C plus D plus E. Am I correct? Okay. Now, so this average is in terms of the addition, plus. But you can also talk about the average in terms of multiplication. So I want to replace these 5 numbers. So can I replace these 5 numbers by some number? Let's call it x, such that you replace each of them by x, so there are 5 of them. Then the product will be equal to the product of A, B, C, D, E. Then for this sense, so each of these x should look like what? It should look like you multiply them A, B, C, D, E together. Is that okay? And take the 5th root. Is that okay? Is that okay? So this is also a kind of an average. This is an average from the plus operation. This is an average from the multiplication operation. Okay? So we call this the arithmetic mean. Mean means average. Okay. And then this one, we call it the geometric mean. Okay? Okay. And then let's assume that we are always talking about positive or non-negative numbers. So let's say all the numbers are non-negative, greater than -0. Okay, then there is an inequality. AM is always greater than or equal to GM. Okay. So what does that? So what in general? What we are saying? We are saying that A1 plus A2 plus ... plus AN. You divide it by n. It is always greater than or equal to the n. So you try to multiply them together, but you take the 1 over nth root. Okay, this is always true. And when will it be equal? So it is an equality, right? It will be equal when everything are the same. So if you think of this, all of them are the same, then it will be A1 times n divided by n. So it is A1 on the left-hand side. For this one, it is A1, 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 A1. So it is A1 to the power n, and you take the 1 over nth root, okay? So it will become A1 back. So this is the case where equality holds. Okay, so let's try to prove it. Let's try to prove it. So to prove this, let's call this statement. Let's give a name for this statement. Let's call this statement Rn. Okay. So we know that R1 is true. We just have one number. It's true. It's true. But then we are not going to use this as the basis case because it turns out that R2 is very useful. So we also try to prove R2. Okay. So R2 is what? R2 is, if we look at A, so we have A1 plus A2, right? You want it to divide this by 2. And then we look at whether it is greater than or equal to the square root of A1 and A2. Is that okay? We don't know. We don't know. But then this one is equivalent to checking whether A1 plus A2 over 2 square is greater. All of them are non-negative. So we square both sides. So it still hold. Okay. It's greater than or equal to A1, A2. Is that okay? So we want to know whether this is true. Okay? Okay? And this is equivalent to checking what? Checking A1. So checking what? Let's see. Checking A1 square plus 2A1, A2 plus A2 square, is it greater than or equal to? We don't know. 4 times A1 times A2, right? Right? So this is equivalent to check what? Equivalent to check what? Check whether A1 square minus 2A1 A2 plus A2 square is greater than or equal to 0, right? Right? Move it back, okay? But then this one is what? This one is equivalent to checking whether a1 minus a2 squared is greater than or equal to 0. Okay? Good. We know that this is true. So this is true. This is true, so this is true. This is true, so this is true. This is true, so this is true. Okay? So we have done a long way. R2 is true. Because, so if you want to write down because this one is true, so this one is true. This one is true, so this one is true. This one is true, so this one is true. This one is true, so this one is true. So R2 is true. Is that okay? Okay. Now to save space, let's prove PK implies P2K. Okay. So because you memorize it by heart. Okay, how about P? Okay, so okay, because okay. Now assume PK is true. So that means that the average of any k numbers in arithmetic part will be greater than or equal to the average for the k numbers in the geometric part. And then we know that 2 is also okay. Okay. So we are considering what? We are considering the case where we have 2 k numbers. So we have a1 plus a2 plus a2k. We want to examine this number divided by 2k, whether this is going to be greater than or equal to the desired form that we want. Okay? Now, let's try to make use of this result. Make use of the past results and also the induction hypothesis to help. So the first thing is, let's make it simpler. 2k numbers, we don't know how to solve, but we know how to solve k numbers. So that makes sense if you partition them into groups of k numbers, right? Okay, so let's partition them into group of k numbers. So we have k a1, a2 plus, so we have this as the first k numbers, and then we also have the last k numbers. Is that okay? And then we want to divide it by 2k, right? Divided by 2k. So what I'm going to do is, I want to divide this by k, I want to divide this by k, and so that we have a division by 2 here. Okay. This is my intention. My intention is, I want to look at this as 2 numbers. This is one number, this is the other number, and this will be the average of these 2 numbers. Is that okay? So this will be greater than or equal to R2 by R2. This will be greater than or equal to the, okay. The average in the geometric part. Does that make sense? Okay? So this part is from R2. But we have not shown, not R2, so this is RK, okay. So we are calling this R. But now, this number is the average of k numbers. By RK, we can show that this will be, this part, this will be greater than or equal to, just this number will be greater than or equal to A1, A2, AK to the power 1 over k. Is that okay? And this number will be greater than or equal to AK plus 1, AK plus 2 up to A2k to the power 1 over k. Is that okay? Okay. Combine everything together. these two combined together will be greater than or equal to, if you multiply everything, these two together will be greater than or equal to the power 1 over k. Am I correct? Is that okay? And then we have a 1 over 2 here. We put this back. So this will be all the numbers multiplied together to the power 1 over 2k. This is the R2k part. Is that okay? So assume RK is true. So in the end, we have a lot of derivation. So we can have R2k is true in the end. So far, so good, right? So just we have one missing link. So we want to show that what? We want to show that pk implies pk minus 1. Okay? Now that is the most crazy part of this proof. Crazy, very crazy. So pk implies pk minus 1. For simplicity, let me change it to the equivalent form. Let's call it pk plus 1 implies pk. Is that okay? The same, right? Okay, so here, so we are going to prove the second inductive case to be correct. And after that, we can have everything finished. Okay, so now assume what? Assume that our statement is R. So R k plus 1 is correct. It's true. So what does that mean? It means that we will have A1. We will have what? We have A1 plus A2 plus everything up to A k plus 1 divided by k plus 1. It will be greater than or equal to, we try to multiply them together, A1, A2, up to AK plus 1 to the power 1 over k plus 1. Is that okay? Now, crazy thing here is, this is true. We can use it. We can now use it. We assume that this is true. We hope to get what we want. We want only to consider only k numbers rather than k plus 1 numbers. So we want to get rid of one number. So the easiest way to get rid of one number, okay, set it to 0, right? But if you set this to 0, then what will happen? Then this will become 0. And this is not what you want. You want to show that it is the product of A1 up to AK. You still want to set it, but then you keep the things that you want. Now, the crazy part is we find a special thing to substitute AK. So here, this is the crazy thing. We set, so we want to get rid of AK plus 1 in a strange way. So we want to take AK plus 1 to be the average of the other k numbers. Over k. Okay? And let us see what will happen. Okay? Let us see what will happen. So then this one, we just substitute this AK plus 1 into this one. So the left-hand side will be equal to what? It will be equal to A1 plus A2 plus dot, 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 up to AK. So we have 1 from this group, and then 1 over k from this k plus 1. Is that okay? Does that make sense? And then you divide this by k plus 1. Is that okay? This is what we have here. Does that make sense? So the first A1 up to AK, so it is A1 up to AK, I multiply by 1. And this AK plus 1, I multiply this by 1 over k. What is it? What is it? What is it? What is it? So this is the average of them. The average, actually this is AK plus 1. Okay, but so this is the average of them. Is that okay? This is the average. And this is very nice. This is what one part of what we want to show, right? Okay, greater than. Greater than, what is it? So this is like A1, A2, dot, 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 up to AK, right? And then this AK plus 1, right? And AK plus 1 will be what? AK plus 1, I don't know. Let me see. Okay, let's write down AK plus 1. Okay, so don't be very hurried. So this is going to be the average, right? And the average turns out to be this AK plus 1 that we are setting. Is that okay? Is that okay? So this is going to be A1, A2, up to AK times AK plus 1 to the power 1 over K plus 1. Is that okay? Is that okay? You have AK here. You have AK here. You can cancel, divide both sides by this part. So what do we have? We will have AK plus 1, this number, to the power K over K plus 1. Is that okay? Is that okay? It's greater than or equal to A1, A2, up to AK, 1 over K plus 1. Does that make sense? Does that make sense? Okay. If you are okay with this so far, could you please raise your hand? Okay, so I'm deleting this AK plus 1 from both sides. Then what do we have? Each side has K plus 1. So I can remove this K plus 1. Is that okay? And this is to the power K, this is the power 1, so I can move the K to this side. Okay? Good, done. This is done because AK plus 1 is the average of the K numbers. We show that it is greater than or equal to the geometric mean of the K numbers. Done. So somehow after some magical cancellation, we have shown that PK is also RK, the statement for the parameter K is also true. So now we have something like, we have a base case P1, or in our case R1 and then R2. And then we have shown that RK implies R2K, and then we have shown that RK plus 1 implies RK. So we can actually show that Rn is also true for every cases. Okay, now, so backward induction actually does not happen very often, but maybe if you want to show correctness of a program, maybe it is useful. So some program, you may first assume that it works for all 2 powers. Like if you are working on merge sort, it works for any 2 powers. Okay, then we know that, okay, if your input has size of 2 powers, then it is working correctly. And next, you can also argue that maybe in your algorithm, if something works for, let's say if it can sort for K numbers, then it can also sort for K minus 1 numbers. Because you just have one number less. You may substitute a 0 there and then apply this one as well. So in that case, you can show that your algorithm actually works for all possible cases. So this could happen in real life situation. But I think this is the most elegant example of using backward induction. And so far, I don't see any other else. Okay. So if you have seen something, or if if I see some other example later, then I will include this in the assignment so that you can try. Okay, that's it. Okay, so that's the end for the class today, and then let's meet again on Thursday. Thank you.